Welcome to this lecture on uncertainty in expert systems. During this lecture, we'll cover certainty factors, as well as provide a brief overview of other expert system uncertainty considerations. Recall that we'd previously introduced expert system frameworks, and thus far we have primarily discussed them in the context of being systems used for deductive reasoning, or for deriving certain conclusions with no ambiguity. In our lecture covering how to build an expert system, one of the considerations for their implementation was the possibility of calculating certainty values for rules that make up these systems. Later, in our lecture on probability fundamentals, we examined how naive Bayes could be extended and simplified using the assumption of conditional independence into the form of this equation for predicting the probability of a hypothesis given different pieces of evidence. We noted here that this form of the Bayes rule was most likely to be used in an expert system framework. We also touched on odds-likelihood ratios as a more versatile and intuitive form of Bayes, often used in clinical or diagnostic settings. And we saw how this alternative form could be used to intuitively calculate and update posterior odds given new pieces of evidence. And we noted some general issues with using the Bayes rule that could make this approach either cumbersome or unreliable in various situations. So now we move on to discussing certainty factors, which can be viewed as an even bigger, simplifying alternative to Bayesian reasoning. Certainty factors are effectively just a number that measures the expert's belief, where the maximum value of a certainty factor is typically +1 for definitely true, and the minimum value might be -1 or definitely false. For example, if the expert states that some evidence is almost certainly true, a certainty factor value of 0.8 could be assigned to this evidence. Importantly, certainty factors are not the same as probabilities, but of course they're conceptually and intuitively related. Mycin, one of the earliest and best-known expert systems, used the following certainty factor values to quantify the level of expert certainty in different facts in the rule base, ranging from definitely, or +1, to definitely not, or -1. In expert systems that use certainty factors, the knowledge base consists of a set of rules that have the following syntax: if evidence, then hypothesis, with an associated certainty factor. Again, this certainty factor represents a belief in the hypothesis given that the evidence has occurred. Over the next 2 slides, we'll examine how to calculate certainty factor values for rules as a more formal and rigorous way to obtain them rather than just estimating them. Doing so begins with 2 new functions. The first is the measure of belief, or MB, which is the measure of increased belief in the hypothesis, or the then part of the rule, given some evidence, or the if part of the rule. This measure of belief is calculated with the following equation, where P of H is the prior probability of the hypothesis H being true, and P of H given E is the probability that hypothesis H is true given evidence E. So back in this equation, if P of H is 1, the measure of belief is also 1. Otherwise, it's calculated as the maximum of either P of H given E, or P of H, subtracted by P of H, and all divided by 1 minus P of H. The logic behind this equation is that if the probability of the hypothesis given the evidence, or PH given E, is higher than P of H, your belief increases. Then we also have the measure of disbelief, or MD, which means the increased disbelief in the hypothesis due to the evidence E. This measure of disbelief is calculated with the following similar equation, where now if P of H is 0, then the measure of disbelief is 1. Otherwise, it's calculated as the minimum of either PH given E or P of H minus P of H, and all divided by negative P of H. The logic behind this equation is that if the evidence makes the hypothesis less likely, the difference is calculated and scaled against the original probability. So these values of measure of belief and measure of disbelief range between 0 and 1. The strength of belief or disbelief in hypothesis H depends on the kind of evidence E observed. Some facts may increase the strength of belief, but others might increase the strength of disbelief. The total strength of belief or disbelief in a hypothesis is represented as the certainty factor calculated by this equation: the measure of belief minus the measure of disbelief, all divided by 1 minus the minimum of either measure of belief or measure of disbelief. Note that the math behind these calculations is fairly simple compared to a more rigorous Bayes rule approach. So let's walk through an example of using certainty factors as a part of rules. Imagine we have the following simple rule. If A is X, then B is Y. An expert may not be absolutely certain that this rule holds. Also, suppose it's been observed that in some cases, even when the if part of the rule is satisfied, in other words, A takes on a value of X, object B can acquire some different value Z. So here we have if A is X, then B is Y, with a certainty factor of 0.7, or B is Z with a certainty factor of 0.2. So far we've examined certainty factors as part of an individual rule. But of course, rule-based systems can involve many rules that work together to apply reasoning. So now let's look at how certainty values get propagated through the reasoning chain. Recall that when the antecedents of rules become satisfied using forward chaining, they fire, subsequently adding new facts to the fact base. These new facts will also have certainty factors. The propagation of certainty values involves establishing the net certainty of the rules consequent when the evidence in the rule antecedent is uncertain. Or, as expressed in this equation, the certainty factor of a new fact or hypothesis being added to the knowledge base is equal to the certainty factor of the evidence multiplied by the certainty factor of the current rule. Here's a simple example where we have a rule, if sky is clear, then the forecast is sunny, with a confidence factor of 0.8. And let's also say that our current certainty factor of sky is clear is only 0.5. Then our certainty in the conclusion H, given the evidence E, is 0.5, which is the certainty in our evidence, times 0.8, which is the certainty of the rule itself, yielding a total certainty factor of 0.4. For this conclusion, the result could be qualitatively interpreted as it may be sunny. On the last slide, we examined certainty factor propagation in a rule with only one condition in the if part of the rule. But let's clarify how certainty factors propagate if there are multiple antecedents connected by conjunctions, in other words, ands. Also on the next slide, we'll also look at antecedents connected by disjunctions, or in other words, ors. Starting with conjunctive rules, we have the following equation summarizing how the propagation of certainty factors would occur. Again, here we have rules with multiple conditions connected by ands, or in other words, we want a certainty factor of a hypothesis given that multiple evidences are true. In general, this is calculated by finding the minimum certainty factor among all antecedents, multiplied by the certainty factor of the rule itself. As an example rule, we have if sky is clear and forecast is sunny. Then action is to wear sunglasses with a certainty factor of 0.8. We assume that the certainty of sky is clear is 0.9 and the certainty of forecast of sunny is 0.7. Now we can calculate the certainty factor for our new fact, or action in this case, being to wear sunglasses. From our equation above, we see that this is calculated as the minimum of the evidence certainty factors, which in this case is 0.7, multiplied by our rule's certainty factor, which here is 0.8, giving us a final certainty factor of 0.56. Now let's look at a similar example, but now using a disjunctive rule, or a rule that has antecedents connected by ors. The only difference in this equation is that instead of taking the minimum certainty factor of all evidences, we instead take the maximum. And here's an example rule that says if sky is overcast, or the forecast is rain, then the action is to take an umbrella with a certainty factor of 0.9. Here we assume that the certainty factor of sky is overcast is 0.6, and the certainty factor for forecast is rain is 0.8. And now we can calculate the certainty factor of our action, take an umbrella, to be the maximum of our evidence certainty factors, which in this case is 0.8, multiplied by our rule certainty factor, which is 0.9, giving us a resulting certainty factor of 0.72. How about situations where two or more rules have been fired that propose the same consequence? Here, the individual certainty factors of these rules must be merged in order to give a combined certainty factor for the final hypothesis. You could think of this as multiple rules firing, and each contributing together towards voting on the certainty of that given outcome. Suppose your knowledge base consisted of the following two rules. One is if A is X, then C is Z, with certainty factor 0.8, and the other is if B is Y, then C is Z, here with certainty factor 0.6. Common sense suggests that if we have two pieces of evidence from different sources, in this case Rule 1 and Rule 2, and they support the same hypothesis, in this case that C is Z, then the confidence in the hypothesis should increase and become stronger than if only one piece of evidence had been obtained. So we can combine certainty factors when multiple rules fire using the following equation. When both certainty factors are positive, then the new certainty factor is just the sum of the two multiplied by 1 minus the first certainty factor. If both certainty factors are below 0, we can again add them together and multiply them by 1 plus the first certainty factor. And if one is positive and one is negative, then we can use this equation. The sum of the two certainty factors divided by 1 minus the minimum of the absolute values of either certainty factor. Stepping back and looking at the difference between Bayesian reasoning and certainty factors, let's just mention a few items. First, probability theory is the oldest and best established technique to deal with inexact knowledge and random data. It works well in areas like forecasting and planning, where statistical data is usually available and accurate probability statements can be made. The Bayesian belief propagation is one of exponential complexity, and thus it's impractical for large knowledge bases. On the other hand, the certainty theory is not mathematically pure, but it does mimic the thinking process of a human expert. Using certainty factors tends to outperform subjective Bayesian reasoning in such areas as diagnostics. Certainty factors are used in cases where the probabilities are not known or are too difficult or expensive to obtain. Their evidential reasoning mechanisms can manage incrementally acquired evidence, the conjunction and disjunction of hypotheses, as well as evidences with different degrees of belief. The certainty factor approach also provides better explanations of the control flow through a rule-based expert system. So at the end of the day, Bayesian reasoning is more accurate and more mathematically correct, and certainty factors are easier to use, interpret, and better mimic the way humans think, which can be either a good or bad thing. In the second part of this lecture, we'll briefly discuss some other uncertainty approaches used in expert systems. Broadly speaking, in expert systems, the probabilities required to solve a problem will need to be provided by experts. An expert would need to determine the prior probabilities for possible hypotheses, in other words, P of H, and P not of H, as well as the conditional probabilities, P of E given H, for observing evidence E if the hypothesis H is true, as well as the conditional probabilities, P of E given not H, if the hypothesis H is false. Users of the expert system will provide information about the evidence observed, and the expert system therefore computes the probability of a hypothesis given the evidence for the hypothesis H in light of the user-supplied evidence E. Of note, there are two main genres of expert systems. Simpler ones are known as monotonic expert systems. Rule-based expert systems primarily use monotonic logic, meaning that they can't retract conclusions or facts once they've been added. Here's a fairly famous anecdote given by Minsky at a 1982 presidential address that illustrates where monotonic logic fails to work well. He gave the example where a human indicates that all ducks can fly, and Charlie is a duck. The expert system then reasons that Charlie can fly. Then the human adds the fact that Charlie is dead. So now the expert system ideally needs to be able to change its conclusion and reason that Charlie can no longer fly, given the additional knowledge that Charlie is dead. However, a monotonic expert system can't learn any knowledge that contradicts what's already known by the system. In other words, you can't replace a statement with its negation. Therefore, the knowledge base can only grow new facts in a monotonic, one-directional fashion. The advantages of these monotonic expert systems is that they greatly simplify truth maintenance, and there's greater diversity of learning strategies that you can use with these systems. In contrast, non-monotonic expert systems can learn knowledge that contradicts what's already known. It does this by replacing old knowledge with new knowledge. The advantage here is that there's increased applicability to real-world domains, and a greater freedom to learn new things. These are much harder to build, but a number of expert systems relying on non-monotonic logics have been proposed. Beyond what we've covered in this lecture, there are some other ways to represent uncertainty in expert systems. One of these is default reasoning. Here we have non-monotonic logic that allows the retraction of default beliefs if they prove to be false. There's also evidential reasoning. This is exemplified by the Dempster-Schaffer theory, which offers a framework designed to handle uncertainty by allowing for ignorance. This is something standard probability and strategies like Bayesian networks struggle with. While other strategies must assign a probability to every specific outcome, even if they're just guesses, the Dempster-Schaffer theory allows you to assign so-called mass to sets of possibilities when the evidence isn't specific enough. Then there's fuzzy reasoning, where a fuzzy set can describe how well an object satisfies a vague property. Fuzzy logic asks, how true is a logical statement? And lastly, Bayesian networks offer modeling of probabilistic dependencies between variables in a directed acyclic graph. Let's conclude by briefly examining some of the trade-offs regarding ways to represent uncertainty for reasoning. When we're dealing with probability or Bayes strategies, the inference process can be highly complex, but you do get quantitative measures of uncertainty. With certainty factors, they're not semantically well-founded, rules have to be independent, and certainty factors have to be available and of a reasonable quality. However, certainty factors allow for rule-based inference, and they're much simpler than dealing with probabilities. With non-monotonic logic, you can represent common sense reasoning, but it can be very computationally expensive. The Dempster-Schaffer theory has some nice formal properties, but can also be complex and computationally expensive. Furthermore, the confidence intervals tend to grow towards 0 to 1, which may not translate into very useful conclusions. With fuzzy reasoning, the semantics themselves are super unclear since, surprise, they're described as fuzzy. Also, you tend to get longer inference chains that become problematic. However, fuzzy reasoning systems are easy to design, and they have intuitive rules that can be useful for some specific applications. Finally, Bayesian networks offer nice theoretical properties combined with efficient reasoning, which has made them very popular. However, they have a limited expressiveness, and they often introduce knowledge engineering challenges that can limit their uses. In general, when it comes to representation of uncertainty, there's the general trade-off between computational complexity versus representational power and precision of those uncertainty probabilities. To summarize this lecture, certainty factors offer a simpler, more intuitive approach to handling uncertainty in rule-based expert systems than the traditional Bayesian approaches. Certainty factors can be assigned using measures of belief and disbelief, and quantification of uncertainty can be propagated through the chain of reasoning in an expert system as rules fire. And lastly, outside of traditional Bayesian strategies and certainty factors, alternative strategies for representing uncertainty in reasoning may be worth exploring, including non-monotonic, Dempster-Schaffer theory, fuzzy reasoning, and Bayesian networks. I'm Ryan Urbanowitz, and thanks for joining me for this lecture. Stay skeptical, curious, and creative.